Complex zeros in the fundamental theorem of algebra. In an nth degree polynomial, it can have at most n zeros. Complex number systems have exactly n zeros and can be factored into exactly n linear factors. The fundamental theorem of algebra states that for every polynomial p of x, its complex coefficients has at least one complex zero. We can also have the complete factorization theorem. If p of x is a polynomial of degree n greater than 0, then there exist complex numbers a, c1, c2, all the way to cn with a equals 0, such that when a does not equal 0, that makes more sense, such that p of x equals a times x minus c1 times x minus c2 all the way to x minus c sub n. To find complex zeros of any nth degree polynomial, we first factor as much as possible, then use the quadratic formula on parts that we cannot factor further. We're going to find all solutions of the equation x to the 6 minus 64 equals 0. There is no good 6th root, so we cannot just add 64 to both sides and take the 6th root. But x to the 6 and 64 are both perfect squares, so we're going to use the sum and difference pattern. And it factors into x cubed plus 8 times x cubed minus 8 equals 0. Now these two, respectively, are the sum and difference of cubes. And I can get those equations to you in class tomorrow. So x cubed plus 8 will factor into x plus 2 times x squared minus 2x plus 4. And x cubed minus 8 factors into x minus 2 times x squared plus 2x plus 4. So we already have two linear factors, x plus 2 and x minus 2. But the other two are quadratics, and these are infactorable. So we have two linear, and we have two quadratics that are not factorable. So we need to use the quadratic formula for both. So for x squared minus 2x plus 4, it goes to x equals 2 plus or minus root negative 2 squared minus 4 times 1. Those are in backwards order, over 2. So it gets down to 2 plus or minus root negative 12 over 2. And we just reviewed how to simplify complex roots. So it goes to 2 plus or minus 2i root 3 all over 2, and we can simplify it one more step further. You get 1 plus or minus I root 3. So that gave us two more solutions. So we'll go back up to x squared plus 2x plus 4. X equals negative 2 plus or minus square root of 2 minus 4 times 1 times 4 all over 2. We're going to work this out. That goes 4 minus 16, which is negative 2 plus or minus root negative 12 over 2. Almost the exact same thing we had before, except it's a negative 2 up front, not a positive. So it goes to negative 2 plus or minus 2I root 3 over 2, which can be simplified to negative 1 plus or minus I root 3. So that gave us 1, 2, 3, 4 solutions, plus our ones from the linear. X plus 2 equals 0, so x equals negative 2. X minus 2 equals 0, so x equals 2. So we got 1, 2, 3, 4, 5, 6 solutions, and we were degree 6 to start. So we have found all of our zeros. Negative 2, 2, 1 plus I root 3, 1 minus I root 3, negative 1 plus I root 3, and negative 1 minus I root 3. Sometimes we will have multiple zeros that are the same. So in the complete factorization theorem, the numbers C1, C2, and Cn are the zeros of P. The zeros need not all be different. If the factor, not in, if the factor x minus c appears k times in the complete factorization of P of x, then we say that C is a zero of multiplicity K. So for example, we have P of x equals x minus 2 quantity squared times x plus 1 to the 5th times x minus 3 to the 3rd. So we get our zeros, 2 with multiplicity 2, negative 1 with a multiplicity of 5, and we get 3 with a multiplicity of 3. The zeros theorem states that for every polynomial of degree n is greater than 1, has exactly n zeros, provided that a zero of multiplicity k is counted k times. So we're going to factor and then find all zeros of the polynomial. We have P of x equals 3x to the 5th plus 24x cubed plus 48x. So we see that they all have an x we can take out, but they can also all have 3 removed as well. And we get x to the 4th plus 8x squared plus 16. Even though it's a higher power, it goes from 4 to 2, so we can factor this. What multiplies the 16, that adds to 8, that's 4 and 4. X squared plus 4 times x squared plus 4. Well, we see the same thing repeating twice. So we write it as 3x times x squared plus 4 quantity squared. This is factored. But now since we want to find the zeros, we set each factor equal to 0. So 3x equals 0, x squared plus 4 equals 0. We're not going to take the higher power, the square, because it's not going to do anything, and we're going to state its multiplicity in our answer. So for 3x equals 0, we get x equals 0. For x squared plus 4 goes to x squared equals negative 4. Square root both sides. And we are getting a complex number. So this goes to plus or minus 2i. Always take the plus or minus on a root. Now these answers, it was squared, so these are happening at a multiplicity of 2. So in total, our zeros occur at 0, 2i. Sorry. 2i with a multiplicity of 2, and negative 2i with a multiplicity of 2. So that gave us 5 zeros in total, and our highest degree, our degree of the polynomial was 5. So just going through some examples, if we have a degree 1 polynomial, such as x plus 5, it's linear, our 0 is 5, and we have only one 0. Degree 2 could look like x squared plus 8x plus 16. We can factor that into x plus 4 quantity squared. Our 0 is negative 4, but we have 2 of them because it's a multiplicity of 2. A degree 3 might look like x cubed plus x. We factor out an x, and when we factor x squared plus 1, it's going to go to x plus I times x minus I. So our 3 zeros occur at 0, I, negative I, and I. 3 zeros. For our fourth degree, you could have x to the 4th plus 8x squared plus 16. We see, and we actually just did this, it goes to x squared plus 4 quantity squared, and we get x plus 2i quantity squared times x minus 2i quantity squared. So our solutions are 2i, the multiplicity of 2, and negative 2i times multiplicity of 2. How we're getting this last line is we already know what the zeros are, and we're putting them back into x minus c. That's what we did on the green as well. If we had solved x squared plus 1 equals 0, we would have got I and negative I. And we just put it back into x minus c. A 5th degree polynomial could be such that x to the 5th minus 2x to the 4th plus x cubed. Factor out an x cubed goes x squared minus 2x plus 1. And this can factor down into x minus 1 quantity squared. So we get zeros of 0, with a multiplicity of 3, and 1 with a multiplicity of 2. We have a total of 5 zeros.